Okay, folks, we're back here for chapter on the inductance chapter. So last time we found that the current is given by this equation here, and I'm going to here write it right in here. Don't forget, this is the current of the circuit that's flowing through the resistor and is flowing through the inductor. It doesn't matter which device we have it, the current is this one. Okay, if you want to find, if you want to find the voltage, right, across each element of the circuit, what we have to do, we have to use the proper equation. Okay, you have to use the proper equation. In the case for the resistor, right? Case for the resistor, we use Ohm's law, which you already know. V of the resistor is Ri. So all you gotta do is multiply that by R, this equation, and we end up just with V. Okay. And when we do that, we get, the behavior, right, of the voltage with time is the voltage in the resistor with time is very similar to the behavior of the current with time, right? And we get something like that. Here you go. The voltage across the resistor starts with 0 and grows up until it reaches an asymptotic value equal to the electric potential of the power supply. Okay. Well, what would be the behavior for the voltage across the inductor, right? The voltage across the inductor is going to be, in order for energy to conserve, right, it's going to be the V minus VR. That's why we get something like that. But you can remember, right, from Kirchhoff's loop law, right? Kirchhoff's loop law, we have to have a conservation of energy, right? We have to have conservation of energy. But there is another way, here you go, let's write that down. The voltage across the inductor can be obtained either from Kirchhoff's loop law or Faraday's law. Faraday's law, right? Which Faraday's law in the format for the inductor, right? For the inductor. So how is that? Let's go back to that equation that we saw. Here's the Kirchhoff's loop law, right? And we have also this one right in here. Okay, recall the current is the same whether it's going through the inductor or the resistor. Okay, I'm going to change the notation here. And copy what we have right in here. let's go to the next line. This negative sign goes outside and it cancels this other one. We are left with this derivative. Okay, and exponential, we're going to get an exponential term, right, minus R over L. And the L cancels out with the L, the R cancels out with the the R cancels out with the R, and we end up having this relationship here. And don't forget, we're getting the magnitude, okay? The magnitude of the VR. Let's put it like that. And note, see that what you have right in here coincides with what you have in our book, okay? It starts with the voltage provided by the power supply and decreases exponentially. So that's the way to get that. Okay, and what we're going to do now we can get into the circuits, still the other case, right? Whenever you are uncharging the inductor. In order to uncharge the inductor, we have this situation right in here. First, we charge the inductor. We produce electric potential difference. And then we use a switch to uncharge the inductor. Remember, we're doing that just like we did for the capacitor, right? Let's do the math. Okay, so we're going to have a loop, a clockwise loop, V sub L, V sub R equal to 0, right? Let's get that. We're going to use, let's copy that. We're not going to get exactly the same current, but there are lots of things that match what we're doing, right? So you go V sub R plus V sub L equal to 0. The electric potential is decreasing, right? Don't forget that at this, the V sub L, the inductor is the one that's acting like a battery, right? But you gotta use the proper equation for that. So we have this situation here. Now the minus sign can go outside this term, right? And LDI, we are separating the variables. Okay, and we do not need this spot. we do not need this. This one we don't need it. Let's say the L goes outside, the R goes outside. Those are the two terms. We still have a negative from this term, and we end up. Let's L over R like that. From I naught to I. We don't have this R here, but we do have L. I naught to I. Apply the limits. The negative sign that we have remains, right? And we are going to I over I naught right here. What goes on the left side is just the T. And we're going to pass the R and the L to the left side, as well as the negative sign. As well as the negative sign here. And we finally have, I'm going to take advantage of this term here. And change it accordingly. Like that. So that's how the current changes as time goes by. Okay, going back to this equation, the current decreases exponentially. And the term that we have right here, I'm going to rewrite it in a different way, is very similar to that CR term of the capacitor, of the charging and uncharging capacitor, right? L divided by R. Okay, is a term that has dimension of seconds. So this term here, we give it a name of tau, right? The constant of the circuit, just like we did for the capacitor. And we can rewrite that tau sub L, right? Let's write that down, tau sub L, since we have a similar tau for the capacitor. And we can erase that, all of that. Just like before, you can get the V sub R and V sub L while the inductor is discharging. Now we are going to look at the LC circuit. Okay? The LC circuit is something like that. You have the inductor here and the capacitor here. And we don't have a battery. Okay, in the circuit, we have a charged capacitor connected to an inductor only. So the capacitor already does the job of the battery, of the power supply. And let's see what type of behavior we get. And by the way, it's a very interesting behavior. And let's see what to, let us see what type of behavior we get. Recall what I said, what I pointed out to you before, right? The behavior of the inductor is exactly the opposite of the behavior of the capacitor. Okay, here you go, those two slides that I displayed to you before, right? For time t equal to 0, the inductor behaves like a broken circuit. But the broken circuit is just like how the capacitor behaves for time much greater than the constant of the circuit. And all the way around. We have a short circuit here for time much greater than L over R and for time t equal to 0. Okay? So the LC, here's the LC circuit. At time t equal to 0, the capacitor is charged, the inductor is not. Let's see, here you go. At time, t equal to 0, the capacitor is charged, but the inductor isn't. And what we're going to do, we're going to have the same equations that we had before with the resistor being replaced by the capacitor. Kirchhoff's loop law, right? We start with Kirchhoff's loop law. Something like that. Let's choose, we close the circuit and we choose this direction for the loop, counterclockwise direction, going from negative to positive. Okay, we have VC. And then crossing the inductor, we have VL. And let's not forget that the definition of capacitance is Q over V, like that. And we replace the V sub C, becomes what? C V sub C is Q over C. We get this relation, and then we are going to get this other relation. Let's not forget, I like to say that this is Faraday's law, right? Faraday's law written in a different way. In the next step, we are going to come up with a relation between I and Q, okay? So let's go back to our capacitor. Notice that at time t equal to 0, that the capacitor is discharging, right? Because the capacitor is discharging, the current must be a negative of dq dt. The negative stays, right? And now we can solve this equation that's going to be rather similar to, well, not quite similar, but it's a equation that solves through separation of variables, right? Okay. And what we get here, we have this negative sign now. Well, we don't solve that through separation of variables, okay? We do something else. We do recognize that we have a negative sign. Let me pass the L to the other side. So okay, this equation is similar to that of an exponential solution, right? But it's a different exponential solution, but is a different exponential solution because we have a negative term, okay? For this equation to be valid, to be valid, the solution, can be like the following. Can be like the following. Okay, it's going to be an exponential RT. And then we have a plus and minus sign right in here. The question is, what's this R value is? Okay, that's the question. So we do like the following, we go ahead, replace the Q in the differential equation, this Q right in here, and this Q right in here. Okay. The Q naught cancels out with the Q naught. And then we have to take the derivative. The derivative is like that. This one here. And the plus and minus R. Or the minus and plus R, right? Let us see if this equation has a solution or not, and if it has a solution, what would be the value R? That's what I'm doing here, Like I said, this differential equation has kind of a solution that's very similar to that of the exponential. But let us see what type of exponential that is, right? We go ahead and assume that the solution is Q naught exponential plus and minus RT, where they are, we do not know. We do not know the value of R yet. We substitute that right here and here, okay? And expand it and look at the consequence. Let's see if we can find out what R is. Exponential, well, in the next line, the exponential cancels out with the exponential. Cancels out with this exponential. Okay. And then we have okay, there was a minor boo-boo here. Let me correct that. Don't forget that this I goes right here in this differential, right? So what we must have here is a d dt with a parenthesis there. So what we end up having here is actually a second derivative. Okay, so second derivative here. Second derivative here. Not a first derivative, but a second. Okay. And now again, notice that how this equation behaves, right? When we differentiate it twice, we get the same function times a constant with a negative sign. The solution states that when you differentiate this equation twice, you go back to the original function, right? Times a constant with a negative sign. Okay, we do know that the exponential behaves like that. Right? If we differentiate the exponential once, you get back the exponential again, times a constant. If you differentiate the exponential twice, we still get the exponential with another constant, right? Behaves like that. But it's a different type of exponential, okay? But it is a different type, of exponential solution. Because we have this negative term here. So let's assume that this differential equation does have this exponential solution. Q naught plus and minus RT, where R is an unknown term. Let's see if we can find out first if this solution satisfies the equation, right? It's going to satisfy, but then what would be the solution? What would be the value for R? Okay, so we start again with the second derivative here. Don't forget we have a second derivative here as well. Okay, I'm going here, second derivative. The Q naught cancels out the Q naught. Okay, and then what we end up getting here when we differentiate the exponential once, let's do that step by step, right? d dt, we are going to get a plus and minus R plus and minus and plus r. Okay? We are going to differentiate it a second time. When you differentiate it a second time, the negative sign here is going to multiply the negative sign of this exponent, okay? And ends up, you know, disappearing, but we get a r squared now. Okay, and now that's the, you know, that was what we got before when you forgot to differentiate a second time, right? So now we are going to cancel the exponentials here, cancel the exponential, okay, and look what we end up getting. We end up getting a square root of a negative number. Okay. And the square root of a negative number is just the constant, the imaginary constant I. And then what we end up getting here? Let's take a look here. Okay, it's going to be something like that. We still use the plus and minus sign. But the exponential of okay, but the exponential of a imaginary number is a linear combination of sines and cosines, of sine and cosine, sine and cosine, okay? So let's just use, let us use, let us choose the solution. Let us choose the solution, the solution for either one. Whether the solution is either a sine or cosine solution will depend on the initial conditions of the problem, okay? What we find out is that for this case, the solution is that cosine, okay? It's possible to do that by doing a lengthier procedure that is in my notes. I'm going to display it quickly here for you, okay? I'm not going to do that because it's going to take us too much time. Okay, so here goes, here's the solution, right? Don't forget that the exponential of minus ix and plus ix is something like that. Okay, and then when you substitute just for cosine and add a phase term here, we find out that the phase term for the cosine is going to be 0. Okay, and don't forget is at t equal to 0. So we can go ahead and write down Q naught Okay. That's what the solution is. And now my tau term is going to be a square root of 1 divided by CL. My tau term is going to be that. CL, square root of CL has the unit, the square root, right, of 1 divided by CL has the square root of time, of seconds. Okay. How do we find Q naught? How do we find Q naught? Q naught? Huh? Oh, we use the definition of capacitance. Or Q naught over V, okay, which is the initial voltage of the capacitor, is equal to C. Q naught is CV. Q naught is CV. Okay, so we can put that in the back of our minds, right? And also remember, right, that let's go ahead get here. The V sub C, V is going to be the initial voltage of the capacitor. Right? And remember that V sub C is Q divided by C, and if you want to know how the voltage across the capacitor changes as time goes by, you get something like that. Okay, Q naught is CV, and we end up having V right in here. The initial voltage of the capacitor, and the voltage keep on oscillating back and forth. Notice that it's just like an oscillating circuit, right? With no decrease in the voltage, no decrease in the charge either, unless we add a resistor. If we do it for the VL, going back here for the VL, V sub L, that's my V sub L. Okay, which end up being the second derivative of Q. Okay. When we differentiate the Q twice, we get a cosine. Okay. The same cosine here. And we also get, since we are differentiating twice, L times C. And we also change the sign when we differentiate for the first time, right? See here. Again, let's do this step by step, right? So here we go. I'm gonna copy and paste right in here. recall that I is minus dq dt, right? And when we substitute right in here, let's do this step by step. We are going to get a plus sign, right? T d to q dt2, okay? And we end up having, when we differentiate the cosine the first time, we get a minus sign. When we differentiate the minus sign a second time, we get a minus cosine. And then we have all those constants that comes along with the solution. Okay, so we can cancel the L here as well. Okay, which, by the way, compare that with the VC. Okay, don't forget that's going to be my initial voltage. This term here that you see is minus the voltage of the capacitor, right? You have to have that to have conservation of energy. V sub C. Okay, so VL is minus V sub C. And again, we have an oscillation circuit, a circuit that oscillates back and forth. That has a very important consequence. This type of behavior has a very important consequence. Because now, unless you introduce a resistor, you can have the circuit flowing forever, right? Energy ends up being conserved. The circuit is going to be oscillating forever. So the next circuit should be the RLC. And when we introduce the R in the equation, the resistor in the equation, then now you're going to have a damping of the circuit. And this type of phenomenon we get also from pendulums, okay?